Okay, there we go. All right, so we'll continue. So that's the idea, that we can measure entanglement, which is a subset of the measurement of the spin correlation. And here's what that picture looks like. I think I showed this already, right? So for spin correlation, we saw that we have the singlet and the triplet state, and that the gluons give us the singular one. So if we look right at the threshold, so in a plot of the scattering angle versus the mass of the top anti-top pair, we want to be right at the threshold, very, very low mass. And the scattering angle doesn't really matter. And then I think I had also shown you could actually go to very high mass and large scattering angle, and you could see something similar, but we'll get back to that. But then the question is, entanglement means, is the system separable? So if it's just a top flying this way, the anti-top flying that way, and you measure their spins independently, or you do some transformation, then the system is separable and you never will measure entanglement. Entanglement requires that the system is not separable, which means there is a spin density matrix that couples the top and the anti-top to each other. And in our case, I had shown you already the spin density matrix C, and here the requirement is that the sum of the diagonal elements is, or -3 times the sum of the diagonal elements, the sum of the diagonal elements is larger than 3, which means this entanglement parameter D is less than 1/3. So what I will show you is this parameter D, which, I don't know if that makes much sense physics-wise, but I know it's related to the spin density matrix. And that gives us the criterion that if we're less than 1/3, less than -1/3, we have entanglement. Okay, but we have to do this at the parton level, so that's where it gets complicated, and that's why I talked about unfolding. And in fact, so this is what we have. So this is at the detector level. This is the distribution I already showed you. This is a cosine phi distribution, right? So this is the angle between the two leptons in the TT-bar rest frame. And you see the data here, and then the different predictions with Powherd plus Pythia, which is our nominal, which is the red one here, and Powherd plus Herwig as an alternative, and then also BB4L. So BB4L we haven't talked about yet. That's the Powherd version that doesn't have on-shell top quarks, but really does the entire, all the way to the W and the B, where you don't assume that you have stable on-shell top quarks, and you really allow off-shell tops and everything else. And you see that actually agrees better with the data. And with this, we can actually calculate the detector level D variable just based on this distribution, right? This thing is not flat. There's a shape here. And this is at the detector level what this D looks like. And you see there is a slope, right? Exactly like we expect. We have much more spin correlation for in the central region. And and also you can see we're now looking here at the very lowest bin, right? That's where the very lowest bin in the invariant mass, the TT-bar invariant mass. Okay, good. And now we can take all of that and we can unfold it to the parton level, and we get this, right? So now here is our magic threshold of -1/3, and we see our measurement is here, right? So this is now unfolded to the particle level. So not the parton level, but particle level. But since we're talking about a leptonic correlation, that should be very close. And then the predictions from the generators are here and here, right? So this is Powherd plus Herwig, and this one is the default Powherd plus Pythia, which is our Monte Carlo. And just like you had seen in the spin correlation, we have more entanglement even than the standard model predicted. But then also very nicely, you can see as we're going away from the threshold to higher TT-bar masses, that the entanglement goes away, which is exactly what we had said, right? That the higher you go, the more the entanglement goes away. That's exactly what our expectation was. Okay, very good. Questions so far? All right, and then this is I think this is already 2 years old now. This was the 5 sigma entanglement by Atlas. And then it took a while, but the CMS measurement is also there. And one of the reasons it took a while is because this is lepton plus jets and dileptons. And you can see this is not just the D parameter, but it also has the spin correlation matrix elements themselves as well, right? So this is actually very nice because you see all the individual contributions and you see the spin correlation coefficient. And then this one is in lepton plus jets. And you can see in lepton plus jets is great because you have much more statistics, but it's also harder because you have one lepton. But then on the other side, which one is the lepton equivalent, right? We have a W boson decay to an up-type quark and a down-type quark, and you have to figure out which one's the down-type quark. So this whole analysis requires more statistics because you have to do it on a statistical basis. But you see also, where is D? Yeah, D is over here, right? So at the detector level, there is a value that's large that agrees with the different simulations. And once you get that to the parton level, it's going to be exactly the same thing. But yes?
Sorry, because in the one slide back, there's a difference between the two generators.
Yes.
There's some discussion about this.
There is.
Has there been resolution or explanation on why they're so far apart?
Not yet, but I'll get to that when I talk about toponium, where that is one of the questions, right? So, you know, this is, of course, why I'm talking about it, right? This large difference, obviously, you've discovered new physics. This difference here is due to new physics. But then, yeah, wait a minute. New physics is only on the Atlas side of the ring, not on the CMS side of the ring. Yeah. But then CMS came out with the toponium discovery. So what's going on there? So yeah, I will talk about that a little bit. Yeah. But on the CMS side, so this is lepton plus jets. There's also a dilepton analysis where you have the two leptons, where again, you do this at the detector level. And there it's not unfolded because really the only parameter we care about is the parameter D. And there what we can do is we take the detector level distribution and we just make a fit for the parameter D, right? So rather than doing the full unfolding, we just do a normal standard profile likelihood fit like we do everywhere else. And that gives us the parameter D. But you can already see here, right? If you look at the distributions, right? Which one am I looking at? All the different distributions, pre-fit and post-fit, you know, they agree fairly well, but even here you see a slope, right? And even here, yeah, you already see there's a, I guess I shouldn't point to that. There's a toponium in there already in the plot. But to hide that, I show you this plot, which I'll get back to later, but you can see even in CMS, the predictions are here, right? So here, the entanglement, no entanglement means subprobable, which means further on the right. And so now here, the more entangled we are, the more to the left we are. And now you see in this CMS dilepton analysis, you see exactly what we saw in Atlas. So the two values are consistent with each other. And in CMS also, we have entanglement that's higher than the standard model prediction. Now it's consistent within uncertainties. Nevertheless, it's exactly the same story. Okay, very good. So far, so clear. And I know we had a discussion about separability, and this is exactly what it is, right? So this is where that comes in. It's the D parameter, and it's not separable, definitely not. But one more piece in that direction that I want to get to, which is, you may have heard about that in condensed matter. People talk about this a lot, which is the Bell inequality. Bell inequality really means not just that you have the spin correlation, but really you have two things happening at different locations that are not connected in any way, shape, or form. There's no field or particle that you can send back and forth, right? And that's Bell inequality. And so that's something that is also a measurement that we can make. And so here I have, this is a plot of a Bell inequality measurement. And if the number is larger than 1, we could measure Bell inequality. If the number is not larger than 1, we couldn't. And so what you see is where we have all of our measurements, we get to 1, but not really bigger than 1. And if we have any reasonable uncertainty, in our current data set, we wouldn't be able to measure Bell inequality because at low invariant mass of the TT-bar system, we just don't have that much of an effect. However, I pointed to this area here, right? So this is now, what is it? Up and down system, but in a boosted top frame. So there we have one top speeds away that way, the other one speeds away that way, and yet their spins are in opposite directions, right? Which is what you're not expecting for highly boosted objects. I made a joke before that, you know, the tops at very, very high momentum are just like neutrinos where they're all left-handed, but that's, you can see here, that's not true in this medium boosted region where we really have the situation where we have both the entanglement where one is up and one is down, and we also have them far away from each other and they're moving away from each other where we can actually test this non-locality, right? Where non-locality means quantum mechanically, you measure the state of one, you instantly know the state of the other, right? At the threshold, we can't do that because they're close to each other. They might be talking to each other. once they're boosted, we actually could test Bell inequality because they're far away enough from each other when they decay that we could test it. So if you're working on spin correlations or entanglement, that's a great thing to do with the HL-LHC data. Or maybe even with run, I don't know if you're working on it. Can you do it with run 3? I don't know. Yeah. This one. I don't know if you have enough events to do that in run 3. Yeah. Or yeah, maybe. Anyway, very good. But so the yeah, I should ask anything, questions? All right. So what I wanted to get to next is the toponium that I've hinted at for a long time, which is if you look at the threshold region, right? If we're pretending this is like charmonium production or B meson production, where the TT bar production at the threshold as we're turning it on, right? We have the, so now not spin but color. We have the color singlet state. We have a color octet state, right? That depends on how you have the gluon coupling. But then those two sum together, and we could have a resonance here, right? So this resonance is a resonance in the color singlet state, which then would also be a spin singlet, and that's the toponium. And conveniently, that would be a spin singlet. So I have this plot here, which I thought was nice, copied from, I think this was Benjamin Fuchs. So here, time goes down. So this is now space is on the horizontal axis, and time is on the downward vertical axis, where what you see is we have an interaction point, X up here, the top and the antitop are produced. They're circling about each other for a little bit of time. A little bit of time, as now you saw, you calculated yesterday, right, is very much too short to actually circle about each other. And then one of them decays, right? So then one of them decays, and then eventually the other one will also decay on some sort of time scale, right? And they decay, and that gives you the W and the B, and then the W decays, and that gives you the leptons or quarks, and that's the whole picture. And then the leptons are the spin analyzers and everything else. And so you can also see this slide is where I got the numbers from for the question yesterday, right? The typical scale at which they're rotating is roughly the Bohr radius. The momentum typically is also 20, and the typical time scale is about 3 inverse GeV. Anyway, so that's the idea. But this is not actually how we got to toponium, right? This is sort of the most logical explanation. If you say everything we've observed in spin correlations is extra spin correlation, extra entanglement, it's got to be something like this. The way it was actually found is in the search for new physics, and the search for new physics specifically for a heavy resonance that only couples to top quarks. And so this is a typical search for a heavy resonance that couples only to tops. So we have this loop here, right? So this is, I drew the loop, but really this is an effective coupling. This is just like Higgs production, actually. Has anybody done the calculation of the Higgs to gluon coupling? I guess we don't do that as you have done it. That's not a homework problem anymore. It's a little complicated, right? You have a question or you've done the calculation. Very good, very good. So it's exactly the same thing here, right? This is a BSM particle, but the calculation is the same. Right, and then this decays. And so this would give you a resonance, which is actually a BSM resonance, as opposed to the toponium that I just showed you. But if you're looking at the signature in the detector, it would look exactly the same, right? In the detector, we really can't tell one from the other. But the way we find it is to go back to exactly what I just talked about, which is the entanglement and spin correlation. And here, the clever idea is to actually make a second spin correlation variable. So the first one is the one we already know, which is this dot product of the two lepton momenta. But now we're doing the lepton momenta each in its own parent top system. But then there's a second one where you flip over one of the top directions and you get a second correlation variable, right? And so here's the picture. So if we have just standard model production that gives you something that's, well, it's flat, especially if you flip one direction, that should really be flat. But then if you have a new physics particle, that's either a pseudoscalar resonance like the A or the A dot top that gives you something that's very strongly angled upwards. But if it's a Higgs-like particle, then it's angled downward. And it's even more strongly so in this flipped angle. And then you can see these are great variables. Again, you're looking at this for a very, very low invariant mass spin, and we do the analysis. And so this is the analysis. And so now this is events. And you can see here we have the helicity variable very close to -1. This is where we expect to see the deviation. And in fact, you see a deviation here at very low invariant mass. Then here we have the intermediate range. And you see something here. And then finally, we have the very high range. And you really see a deviation here. And so this is why you can see it doesn't agree with the standard model prediction. But if you're putting in this little toponium resonance, you actually see it agrees very well with the data. But as I just showed you on the previous page, it could actually be either toponium or that we just found a new BSM particle, a new resonance. And then finally, to do this sort of analysis, we do a profile likelihood fit. Who's done a profile likelihood fit? I should ask. Who's done a profile likelihood fit? One. Yeah. So profile, actually, I don't know if you guys will talk about profile likelihood fits much over the next 2 days. Where's Phil's not here? You're not? No? All right. Anyway, profile likelihood fits is what we need nowadays to really get most of the precision out. So we have ±1 sigma uncertainties for everything. And then in our likelihood fit, we allow the data to not just shrink the parameter of interest, but also to constrain all of the systematic uncertainties. And we add control regions to constrain those systematic uncertainties. And that's how we get to from being very dependent, having very large modeling uncertainties, detector-related uncertainties, how we get to having a very precise measurement, because you can see, for example, here, this is just comparing the BB4L, which is the allowing off-shell top quarks, and really having a correct prescription of those, and comparing that generator to the default POWHEC. And you see this difference between the two generators is constrained by quite a lot. And that constraint is what allows us to make this very precise measurement. And then there's many other systematic uncertainties here. A lot of them are related to the top quark modeling, right? There's one on the Pythia versus Herbig. So this is also very strongly constrained. That's the parton shower, right? You can imagine we're very, very dependent on the modeling of the parton shower and many other ones. The other thing that you can see here is there's solid circles and open circles. And the difference there is the solid circles are generally closer to 0, and the open circles are generally further away from 0. And the difference there is that in the open circles, we have not allowed for the presence of the eta, and we've done the fit without having an eta in the fit. And the solid circles are including an eta top in the fit, right? So that's how we get to a cross-section for eta top. We include it in the fit. And then finally, we can actually probe, is it a pseudoscalar or what is it? Yeah, exactly. Scalar versus pseudoscalar, and just measuring the cross-section. And you see on the scalar axis, right, the standard model is here. There is no pseudoscalar or scalar, and the measurement is here. So it's more, we favor a pseudoscalar, and the scalar is still consistent with within one sigma with the standard model, right? So this is how we get to toponium. And because we've done this whole analysis with spin correlations, how we have toponium's got to be a pseudoscalar, which is what we expect, right? That's why it's called the eta. Yes. Sure. Yes.
The next slide, or say one standard deviation. This is each standard deviation for this inner parameters, or for the profiling, or what?
Yes. So this is right. So profile likelihood means we allow this parameter to vary independently. We allow this parameter to vary, and we allow all of the systematic uncertainties to fluctuate. And so then we really do a 250 dimensional fit. Yes. Sure, but the fit will constrain that, right? That's not going to be allowed. Right, but they're all constrained as Gaussian uncertainties. Right? If I go 5 sigma away in one parameter, I have to somehow make up for that in all the other ones, and that's very, very unlikely, right? The minimum is going to be when all of those systematic uncertainties are close to 0. Not well. Yes, that's a different discussion. Yes, yes. But yes, one of the things is how do we do this sort of profile likelihood fit, right? Since we talked a little bit about Tevatron versus LHC. In the Tevatron days, this was not possible. We were just sampling from the distributions, and there's just no way to do that, to compute that likelihood. Now, we really do this, well, not analytically, but analytically as much as possible. And we have much more computing power, and that's really what makes this possible, right? It's modern techniques for integrating 250 dimensions. Are you going to talk about integration? You already have talked about integration. Yeah, very good. So yes, exactly. Those techniques are what we're using here, MC-MC integration. Okay, very good. So now I want to get back to the plot that I already showed you, but without blanking out all of the relevant information, right? So here is now the result without the toponium, where you see we have an excess compared to the generators that we have. And now if you're putting in that there is toponium, right now the prediction, all of these dots include the toponium. So since toponium is the pseudoscalar, all of that gives us spin correlations. So all of the predictions shift over a little bit, whereas data stays exactly where it was before. And so now you see exactly this debate. All you need is toponium, and we agree perfectly with the prediction. Oh.
So just to be clear, this is adding a semi-stable topology.
Yes.
Which we know does not exist.
Yes. Yes. So of the discussions that there are, right? So I mentioned Benjamin Fuchs by name because he's sort of an experimentalist at heart, but he's a theorist where he does what I always say, I'm not allowed to do it, I'll do it anyway, right? It's a particle that everybody agrees does not exist, and we have it anyway in the fit. And it gives you beautiful agreement. This is why I like it as an experimentalist. Yes. We will find out later this summer. As you can imagine, that's a very hot topic in Atlas right now. I've seen the plots. Actually, I haven't seen the plots. I've seen predictions for when the plots will come out. So later this summer. Okay, so other questions before I move on to the next topic? Okay, so the next topic is 4-top. And before I show you the slide, let me ask you, if there is a BSM particle, right? So if it really is an A or an H rather than a toponium, if it's a BSM particle, does the cross-section go up? Does the TT bar cross-section go up? Yes, it has to, right? If you have a new exchange particle, the cross-section has to go up. If there is toponium, if it's a TT bar bound state, does the cross-section go up? No, the cross-section doesn't go up because in principle, all of the calculations that everybody does, they already include any possible effects of bound states, right? That's why we talk about resummation and everything to model the turn-on curve properly. And if there is a bound state, that's sort of on average included, right? So one of the big things is if we could only measure the top pair cross-section to, what is it, 8 femtobarns out of 1,000 femtobarns, we could figure it out, but we're far away from having a better than 1% measurement. However, why do I say 4-top? 4-top is great because it has the exact same vertex. I have 1, 2, 3, 4 tops here. Here we have a loop. To get to 4-top, all I have to do is break up the loop. Boom. So now we have a new physics particle that couples only to top and decays to top. So it only couples to top, and we have 1, 2, 3, 4 tops in the final state. So that's 4-top. And so here, for sure, we should actually see the particle. And if there is toponium at the 8 femtobarn, well, it's not exactly the same production mode, but if it's at the femtobarn level, maybe we would see it here. And then those of you who already know the story, 4-top actually has been measured very, very recently. And if you followed the story, you know the measured cross-sections are all above the standard model prediction, right? So the standard model prediction is somewhere around 12 femtobarns, and all of the measurements by both CMS and by Atlas and the CMS combination and the Atlas combination are all above the theory prediction. So you would think that rules out toponium, and it means we've discovered a BSM particle that's a pseudoscalar. right? Because it would be exactly the same thing. If there is a toponium resonance in photop production, that shouldn't change the cross-section. It should just change the spin correlations. If there is a new physics particle, the cross-section will go up. Now I'm being a little facetious because this is probably not that, but I don't really know. Okay, and I'm going a little fast because I'm running out of time and I have a bunch of other topics still to cover. But if there's any questions here. All right, and in fact, this shows a theory prediction that is all the way as recent as 2022. This was just updated, and it was just updated and the uncertainty went down and the central value stayed the same, or if anything went down. So the theory prediction just got more precise with a smaller uncertainty. So we're, yes. Oh, everything is profiled. Yes. 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 And by far the largest uncertainties are related to the background modeling and the modeling of the top quark final state. Right. And in fact, this measurement here, this is very interesting, both on the Atlas and on the CMS side, because these measurements were not possible in run 2. They were not possible. Both collaborations published papers claiming evidence for 4-top or sensitivity to 4-top and then moved on, right? You can see here all of these, including making combinations. And then, oops, a year later, we submitted another paper which then had observation, and same for CMS, right? This is a tiny uncertainty for a paper that came out. Actually, this came out later in the same year as the combination, right? So this is very interesting. Why? How was it possible that we went from not really having sensitivity to suddenly having sensitivity? And the answer to that is B-tagging, right? Who's worked on B-tagging? Anybody worked on B-tagging? Oh, very good, a few people, very good. Have you worked on the calibration of the recent taggers? No? All right, so B-tagging, just for everybody else, just a quick review, right? So we have a primary vertex. This is where, so in this case, the protons come from into the plane and out of the plane, they collide. Then we have a B meson or some particle containing a bottom quark that travels some distance, you know, a millimeter, the lifetimes are long, and then it decays, and the decay gives us charged particle tracks. So the charged particle tracks, we can reconstruct them and we get a secondary vertex, right? If we get a secondary vertex, that's a B-tag. Or every once in a while, maybe we only have one track. If we only have one track, we try to extrapolate this track backwards to the primary vertex, right? At the primary vertex, there should be lots and lots of tracks, these prompt tracks from the primary vertex. And if there is a distance here, an impact parameter, we can do impact parameter-based B-tagging. So that's great. And these are the basic algorithms, right? At the tevatron, our B-tagging efficiency was typically around 50% for events for jets that have B quark, and about a light quark rejection of a factor of 100. At the LHC, we had better silicon detectors, more layers. So for the same light quark rejection, we were able to get all the way up to 70% B-tagging efficiency, right? And at least when I was working on the tevatron and the LHC, and I thought, great, that's the end of the story. And we can't do much better than this because that's the fundamental physics. And I don't know if you will talk about this in machine learning. B-tagging is the big success of machine learning, right? And so what you see already, this is just Atlas, but it's a very, very similar story for CMS. And so this is now comparing the different machine learning algorithms over time, right? So this is improvements in machine learning algorithm. Already the very first machine learning algorithm, right? So this is charm quark rejection and light quark rejection, right? So charm quark rejection is, so this is about 10% for charm quarks. And what is this one? This is about a factor of 300 for light quarks, right? So for a 70% efficiency, this is already a factor of 3 better than what you get from just secondary vertex and impact parameter, which, how is that even possible? And maybe you argue, well, you have some correlations and so on. But then you see, we keep going up, right? Over the years, we keep going up. And then the modern B-tagging algorithms are, for that 70%, we have a light quark rejection of over a factor of 2000, and even a charm quark rejection that is almost approaching what we could do with light quark jets beforehand. Which, to me, that's the big success of machine learning, because you go far, far beyond just secondary vertex and impact parameter. You put the tracks, track uncertainties, all the vertices, and the hits in the silicon detector, their uncertainties, and everything else, the efficiencies, load up the machine learning algorithm with all the information that you have. And you can see from the slope here, I thought we couldn't do any better. By 2019, I thought, oh, we are doing so much better. This is the end of it. And then we had this one here, and I thought, oh, that's got to be the end of it. But you can see we're doing so much better here. So you can already see there's no way this is the limit either, right? So when we talk about machine learning and AI, this is the slope that convinces me that even here we've just started. There's a lot more to gain, not from the physics that I can put in, but just from having smarter machine learning algorithms. And what is this one? This is the graph neural network. What is DL? DL was at some point we had a BDT. That's not even in the plot anymore. I think this was deep learning. Yeah, this is just a deep learning algorithm. And then we had the graph neural network, which is a much fancier algorithm. Anyway. How much does it? I think this is all trained on TT bar events. So this is all trained with exactly the same Monte Carlo. The main thing that changed with the Monte Carlo, I think here we had 20 million TT bar events. Now we have 200 million TT bar events. It's calibrated to data. Oh, but you're right, because it's TT bar, there's probably a lot of data in there as well. Yes. Yeah. Okay, very good. Other questions on B-tagging? And I'm assuming you hear a lot more about machine learning over the last 2 days, or tomorrow and Thursday. Very good. Will you talk about B-tag? You may not know what everybody else talks about. Okay, yeah. All right, so then finally, I want to get to top quark mass. And first, I want to get to, since we talked about boosted jets, we talked about substructure, I want to talk a little bit about combining everything we just talked about, which is profile likelihood fits, with top substructure, which we heard about last week, right? Where if you have a boosted jet, if you have a boosted top quark, then we have the decay products inside a large radius jet. And we can reconstruct the large radius jet, and we can measure the mass of the large radius jet. And so that's what we have here. And we have the reconstructed mass of the large radius jet. And you can see here, the mass reconstruction algorithm is now so good that even for a change of only a GV and a half, you can see very, very big shape changes, right? And so this is great in our analysis, where again, this is calibrating this and refining the large radius jet algorithms to such an extent that we're now sensitive at this level. And we can have confidence that this is well described by data, right? So this is, again, PowerQ plus Pythia. So we're using the hadronization model in Pythia, and we really find very good agreement. But then the key to getting a very precise top mass out of this is to do the profile likelihood fit, right? So we take this distribution, we do the profile likelihood fit. And then this is the result of the profile likelihood fit, right? So now you see we have all the systematic uncertainties constrained because they're all constrained in the fit to data. We have thousands of data events in every single bin. So all of the systematics are constrained to, what is it? Square root of 1,000 is 3% or so. That's why this is a very small uncertainty here. And everything agrees fairly well, right? There's one that's an outlier, maybe this one. That's roughly what you would expect, right? That back of the envelope, you should have, 68% of the data points with errors should be inside the band. And that's exactly what we see. Okay, and then if you look at this, this is a, wait, did I even not put the number here? Geez. Oh, no, that's this one here, right? So this is a measurement with a total uncertainty of half a GeV. Getting a top mass uncertainty of half a GeV. 3 years ago, we didn't think that was possible. And now, I think there was a CMS measurement already with early run 3 data, no, with run 2 data. And now we have an ATLAS measurement with boosted jets. So now we're routinely measuring the top mass to half a GeV. But now the caveat comes in that this uses profiling of all the generators, comparing different models, and all of the detector stuff. And in fact, I have a profiling plot here as well, right? So this is the way ATLAS makes these plots, where you see how much the systematic is constrained by the bars here. And then the blue versus orange show you what the impact is on the measured mass. And you see the ones with the highest impact on the measured mass is the final state radiation, right? Just like it was in the other measurements. But here that makes sense because we're looking at boosted jets. And then a lot of jet energy uncertainty, and then parton shower shows up in multiple places, right? All of the stuff that you would expect. And then one more just to say that blue means a shift makes the mass go down, and red means a shift makes the mass go up. Okay. All right, and then this was the a profile likelihood fit, which means we're measuring the mass directly. And measuring the mass directly, we used to call Monte Carlo mass, but we don't call it Monte Carlo mass anymore. We call it direct measurement, right? Which comes from profile likelihood fits, or it comes from anything that compares to putting a parameter into Powherd Pythia that we call top quark mass, and then scanning a likelihood through all the different masses, right? So this is why we call it Monte Carlo mass, because it's a parameter in the simulation. And you can see we have from the LHC combination all the way back in run 1, we have an uncertainty that is as small as 0.33 GeV, right? So this was very, very small uncertainty, and the central value is 170.5. And we did a world combination, which includes the tevatron, where at the tevatron, the top quark mass was measured slightly higher. So the central value is shifted up. And well, I guess in this case, it includes only the 7 TeV data, so it also has a little higher uncertainty. Anyway, but you see within Atlas and CMS, all of these things are very consistent. And you can see all of the different 13 TeV measurements, both by CMS and then in the middle here by Atlas, right? And they're all consistent with this 172.5 GeV, roughly. Okay, and I heard that you mentioned the tevatron, so I added the tevatron once more. If you just look at the tevatron combination, that's all the way over here. And it has a much larger uncertainty of, wasn't that in here somewhere? 0.75 GeV. So it's, 3 sigma away. But this is a little like the CDFW mass, right? Where it doesn't agree with any of the other measurements. So there's probably something not quite right, but you can't really put your finger on anything that's wrong. Here, I know because I've been at the tevatron, all of the generators are old. All of the reconstruction is old, right? There's no anti-KT jet algorithm that we're using, right? A lot of this is reliant not just on data that was recorded 15 years ago, but it's also based on Monte Carlo that was generated 15 years ago. And so you expect there to be a difference, that there's some bias here that we're just not accounting for. But we can see different experiments, Atlas and CMS, very, very different final states, all measure something that agrees. And many, or maybe most of these measurements were done blindly, where everything was agreed upon, was reviewed in many different levels before we open the box and get the actual mass out. Okay, so next step, Monte Carlo mass versus pole mass. I know you heard about that already. A little bit, yeah. So I have a pole mass as well. So at the LHC, we don't worry about pole mass versus MS bar mass. As a theorist, you worry about it. As an experimentalist, I say, oh, you just do a translation. There is a way to get from pole to MS bar mass, right? Yeah, there's no way to get from pole mass to Monte Carlo mass. And so that's why we have a separate measurement, right? And so if you look at all of the different measurements of the pole mass here, we have to unfold something to the parton level and really compare it to, for example, next to leading order or next to leading order predictions. And that's how we get the precision here. Now, having to do that unfolding, you've already seen that gives us additional uncertainties. So here you see all of these error bars are larger, right? The most precise one is this one here that is down to 0.8. And then I think some of the Atlas ones here, yeah, the Atlas and CMS ones that use a top quark pair plus jet differential distributions that are about 1 GeV or so, a little higher. Nevertheless, they're all also consistent, which is, for a while, that was one of the big discussions where I think the argument was the difference between pole mass and Monte Carlo mass is maybe 0.5, but probably smaller, 0.5 GeV or smaller. Okay, questions about top mass? Anything else I should discuss about top mass? Yes. Oh, sorry. We use the Powherd plus Pythia generator. So it's a parameter inside PowHack, because PowHack gives us the tops. So if we're using PowHack plus Herwig, again, it's the top mass that we're putting into PowHack. And as far as I know, if you put a mass in PowHack, it's the same mass in Pythia, but the decay is handled by PowHack, so it shouldn't make any difference. Do you have a question? Somebody else? Yes. Yeah, so that's why we comparing PowHack plus Pythia and PowHack plus Herwig is always a big discussion. In fact, for a long time, CMS wasn't doing it, and now Atlas isn't doing it anymore either, because the argument is that it's really a completely different model tuned completely by itself. So you're really assigning an uncertainty to some random difference that you can't really quantify. And one of the big efforts that we've been going through at the LHC, not just in the top group, but also elsewhere, is very specifically writing down what physics effect is each systematic uncertainty accounting for. And we've done much better at that, but there's still a long ways to go in that as well. But the idea is getting rid of sort of random things of just comparing two things. You know, Pythia and Herwig have both been tuned to the data over the last 20 years. They should both agree perfectly. If you take the difference of them as a systematic, sure, but you're really just, you know, it's two different collaborations, interpretation of the data, not really a systematic uncertainty. Okay, so finally, I think I have 20 minutes left. Finally, I get to heavy ions, and even there, QCD, I get to QCD. I get a little bit to what the FRIP physics is about, which is heavy ion collisions, but not really. And even then, I don't talk about heavy ions because I want to talk about top quark physics in heavy ions, which is, right, the whole point of having relativistic heavy ions. First at RHIC, but RHIC didn't have high enough energies, but at the LHC, we have high enough energies where we have the two oblong shapes of the ions colliding. And when they collide, they give us a quark-gluon plasma, and then everything expands and we get hadronization, and then we see many, many, many particles in the detector. And even though we see many, many particles in the detector, by now we have sufficient sophistication in the reconstruction that we can identify high PT jets and leptons, and that allows us to reconstruct W bosons, bottom quarks, and top quarks. And so that means we can look at top quark physics in a heavy ion collision, right? And top quark physics, the tops are produced somewhere here, they travel some distance, then they decay, and they give us a W and a bottom quark. So if we want to study heavy ion physics or the quark-gluon plasma, it's the earliest times in the quark-gluon plasma that are studied by tops. So that's really, as a probe, they're great. Now, it's very hard to do anything because that probe just doesn't get produced very often, but at least in principle, it's there. And to do there, the first step we had to do, this is what I already showed you, is proton-proton collisions at the heavy ion collision energy, which is 5 TeV. And both Atlas and CMS have made these measurements of the production cross-section. And you can see we're agreeing fairly well with the predictions, although here you can see we have quite a variation depending on which PDF set we're looking at. And what we've done then is we do the same analysis, but in lead-lead collisions. And so there we have Atlas over here and then CMS over here, where we have two different analyses on the CMS side. And you can see we have significance, 4 to 5 sigma for expected and observed. So this is really actually seeing top quarks being produced in heavy ion collisions, which is great. Okay, questions about heavy ion physics? All right, then I want to get to QCD. And what I want to talk about in QCD is you've already heard from Matt about jet physics, cross-sections, jet cross-sections. You've already heard about PDF fits, alpha S. Instead, what I want to talk about more is substructure and some of these event shape variables or jet shape variables that give us information about what the physics looks like inside jets. And so the first one is this measurement by Atlas, which looks at what is called the track function, which is charged particle tracks inside a jet. So we're looking at jets. You can see these are very high PT jets in bins of PT, and then comparing between different predictions right? So this is Sherpa predictions, but then also Pythia and Herwig, and comparing that with unfolded data. So this is now, again, unfolding where we have jets that we have to reconstruct. We find charged particle tracks inside the jet, and then we have to unfold that fraction. What's the transverse momentum fraction carried by the charged hadrons inside this jet? And you see there's a characteristic distribution here that we're observing in data. And you can see the predictions all have a different shape, a slightly different shape, but you see the systematic uncertainty is at the order of 10% or so. And more importantly, we can take this analysis and then we can try to look specifically for gluon jets. So we can tighten our cuts a little bit so that we have fewer events, but we're now looking mostly at gluons. And you can see very interestingly, if we're trying to look mostly at gluons, the systematic uncertainties get bigger, but also the disagreements between the predictions and the data get bigger, right? And so this is when we talk about tuning generators and getting very precise QCD results for very different applications, we have to take one step beyond just measuring cross sections and measuring jets, and we're looking at event shapes, or in this case, charged particles inside a jet. And the other one in that direction is isotropy. So for example, not just inside a jet, but looking at what does an event shape look like if we have a simple dijet event or 3 jets or many, many jets. Again, there's a probability to getting each of those, and we should be able to observe what they look like. And traditionally, we've done that with what we call the thrust variable. And the thrust variable is just, you look at, for example, if you have a jet, you define an axis and you want very little momentum transfers to that axis. And if you've minimized the transverse momentum to that axis, or if you've maximized the longitudinal momentum, that's the thrust axis. And then the momentum in that direction is the thrust, right? So this is what T is. You're maximizing the momentum in the direction of the jet. And what that means is if you have something where everything is back to back, that's the maximum thrust, and you know what the axis is because it's this axis. If you have something that's oblong, it's slightly smaller. And if you have something that's completely round, then the thrust is a half because you can't define a direction. It's some random direction and it's a half. And just like with machine learning, we can do the same way. Maybe I should ask, who's worked with thrust before? Right? So I don't want to be too derogatory, but this is the 90s and the 2000s variable, right? This is state of the art 20 years ago, 15 years ago. Maybe not 15, maybe a little less. Yeah. Oh, yeah, when it was defined. Yeah, but I know this was heavily used at the Tevatron, for example, and also in the early LHC analyses. Now what we do, we go to the next level, which is we put in machine learning algorithms or variables defined based on machine learning, and that's Earth mover. So Earth mover is, who's heard of Earth mover distance? Yeah, so Earth mover distance is very simple. You have buckets of dirt, and if you have 1 bucket sitting here and 4 buckets around, what's the minimum energy required to distribute this bucket into the other 4? That's Earth mover distance. I have some distribution of dirt, and I want to distribute it in some different way. What's the minimum energy required? And turns out that's a very useful description in machine learning. And so what we've done is we apply that to particle physics. And so now we don't have Earth, we have energy. So conveniently, we keep the same acronym. We keep calling it EMD. It's just the energy mover distance. And so again, the one that we're specifically looking at here in the paper that I'll be describing is where we have something that's close to a circle, right? So we have 128 points on a circle, but you could have any number of buckets that you want, right? You could do this with 2 buckets, with 4 buckets. We're distributing all of the energy. The energy in this case is jets, right? So clearly, if I have back-to-back jets, I have to distribute them over 128 buckets in a circle. That's going to give me a very different variable than if I have a lot of jets. They're already distributed, right? I don't have to put much energy in. And that's the way we can describe this. And that gives us very nice distributions where I can probe generators very, very sensitively, right? So here, for example, this is one of those variables. This is the EMD variable, which is distributing it over a ring of 128 buckets. And you can see the distribution is good, except at the very low region and at the very high region, right? So here. And when this is 1, I'm really very sensitive to having to distribute a lot of energy over all the buckets. And that's where all of the different generators here, Sherpa, Herwig, and PowHack, really give me large differences. Of course, this is also where the uncertainty is large, right? And this, by the way, was already unfolded to particle level, right? So this is now machine learning, variable, unfolding, and comparing to generators. All right. Oh, I'm actually good on time. So I have one more, which is something that I've worked on, which is, I know we've talked about Monte Carlo a little bit. I don't know how much Phil talked about the challenge of Monte Carlo, which is, I just told you that we have 200 million PowHack plus Pythia events in Atlas. That was a gigantic effort to get all of those 200 million events. And it would be nice if Atlas and CMS could share those events, if we didn't all have to generate 200 million events on our own. And in particular, what happens a lot is I generate my first 50 million and then I discover a bug, right? And then I have to regenerate everything. That happens more than you would think. And so what I've worked on is actually common Monte Carlo, where we generate the exact same particle level Monte Carlo, which in this case was PowHack plus Pythia, but also Sherpa, with exactly the same settings for both Atlas and CMS. And then we give it to each experiment, and each experiment runs the detector simulation on their own. So that's a great way to save a lot of CPU hours in the generation. And this is going to be even more relevant as we get into the future, right? We've talked about already, I've mentioned the WB Monte Carlo, which has off-shell top quarks. That takes forever to run because getting those off-shell top quarks takes forever. But then we also now have the next to leading order Monte Carlo with parton-shower matching. That's both for Higgs production, but now also for top pair production, takes even longer to run because it's next to leading order. And so something like this common Monte Carlo would be even better. And so what I'm showing you here is to have PowHack plus Pythia and Sherpa running it once through the Atlas framework. So this is really taking the settings and running them all the way through the Atlas framework, and then taking those exact same settings and running them all the way through the CMS framework. And you can see within the statistical uncertainties, within the Monte Carlo statistical uncertainties, they actually agree. And this already took us, I think, 3 years to get to the point where all of those, hundreds of little parameters within Atlas and hundreds of little parameters within CMS all agree with each other. But it's possible. And then one more, just comparing, right? So now we have the common Monte Carlo, which we generated, and the default Atlas Monte Carlo, the default CMS Monte Carlo, and the default Pythia. And here now I'm comparing it to unfolded top quark pair production data. So this is a TT bar invariant mass, right, at the very low region where we started here, where just like before, all of the predictions are below the measurement, and the PT of the hadronic top in this case, where everybody's probably heard about top quark PT mismodeling, right? That's been around for a long, long time. And we can see that still here in the unfolded data. And the only one that's really modeling the top quark PT properly is Sherpa. Okay, any questions about Monte Carlo, top quark Monte Carlo? Because they've paid a lot of attention to making this match properly. It's the interface between the matrix element and the parton shower. And if you can pay a lot of attention to tuning this up properly, you get the right distribution. So I don't have Herwig in here. The default Atlas PowHack plus Herwig also gives a better modeling of the top PT distribution, but it disagrees in many other distributions, so we don't like Herwig. Whereas Sherpa actually agrees in many of the other distributions, which I'm sure there's a little bit of black magic in there, but it actually works. Yes. Could be, yeah. That it's a different matching prescription, yeah. Okay, so with that, I already have my conclusions. And yeah, many measurements. And in fact, who's already working on run 3 measurements, right? We have 220 inverse femtobarns I showed you. We're going to have a lot more coming out over the next few years, right? And not just measurements, but also searches. So one of the things that I'm doing is, I talked about all of the top quark measurements here. What I'm doing right now is actually also a search, right? Many searches involving top quarks, and that's all going to come out. That's already started. Many interpretations, as I mentioned at the beginning, I didn't talk about EFT at all. EFTs are a huge program, not just in top, but also in electroweak and in Higgs physics. And that's really trying to figure out how to get the most sensitivity to new physics out of all of the precision measurements that we have. And EFT already implies global fits, not just PDF fits, but also field theory fits. And then generator tuning, I mentioned that a little bit. And then finally, the HLLHC is coming, and the HLLHC, right? So we have, what do we have? We have top quark physics for another 15, 20 years. We have QCD physics for another 15, 20 years. And then basta. If the FCC starts, not if, when the FCC starts, when the HLLHC shuts down, we have an electron-positron collider, no longer a proton-proton collider, which means, especially at the beginning, there will be no top physics at all because we just don't have enough energy to produce any tops. And even QCD physics will be limited to having electrons collide and producing quarks and studying jets. So all of the beauty with the PDFs and really understanding things in detail, heavy ions, all of that will go away once we start the FCC. Hopefully there will be an FCCHH eventually. I don't know if you will talk about FCCHH, but that's many years in the future. And same thing, right? If, in the US, there was just the mention of the muon collider that should be built. But again, that's a lepton collider, right? So really, I'm claiming that right now, this is the golden age of both QCD and top. You're living in the middle of it. Let's make the most of it while we can. And this is where I'll stop. All right, more questions? Yes.
Going back to that I-128 variable.
Ah, yes, very good.
I need that with sensitivities, you're like, just the jets. It's going to be a lot of work to distribute 2 jets into this, but also a lot of work to do 3 jets and 4 jets. So I would expect them to be close to 0. Whereas if I had left them, say, then I would have much more sensitivity to these smaller jets. What we're going to be.
That's an excellent question. And in fact, what you're showing me is that I skipped over much of what's in this paper. The paper actually had the I2 as well, and I think I4. And I just liked the I-128 because I can easily picture the ring and distributing buckets across the ring. But yes, exactly. So this is very sensitive to having many jets and having very few jets. But if you want to look at 2 versus 3, I2 or I4 are much better. And they're in the paper. Very good. Yeah, 128 is smooth, approximately. As far as ChatGPT knows, 128 is infinity.
Okay, so let's thank Reinhardt again. And let's take a break for 20 minutes. And so be back at 2:30 for our last lecture. So I can